Something doesn't add up about our universe, and the deeper scientists look, the more confusing it gets. Right now, there's a cosmic disagreement so big, it's shaking the foundations of what we know. We call it the Hubble Tension, two different ways of measuring how fast the universe is expanding, but they give us two different answers. And this isn't just some tiny rounding error, it's a gap that shouldn't exist, one that defies every explanation we've thrown at it. So why can't we crack this puzzle? From hidden forces reshaping space itself to flaws in our most trusted cosmic yardsticks, here are 25 reasons this mystery has left even the brightest minds in astrophysics completely stumped. At the heart of the Hubble tension lies a stubborn cosmic contradiction. On one hand, we've got our most precise snapshot of the early universe, the cosmic microwave background, or CMB. This afterglow of the Big Bang tells us the universe should be expanding at about 67 kilometers per second per megaparsec. But when we look at nearby galaxies using cosmic lighthouses like Cepheid variable stars and exploding supernova, we get a different number, roughly 73. That might not sound like much, but in the world of cosmology, it's a glaring inconsistency. These aren't just minor errors in measurement, they are fundamentally different results from two of the most reliable tools in astronomy. It's like checking the same speed with two different radar guns and getting answers that refuse to match. And here's the real kicker. Both methods have been refined over decades, tested again and again, and yet the gap persists. If our measurements are correct, then something crucial is missing from our understanding of how the universe works, maybe even rewriting the rules we thought were set in stone. One of the biggest wildcards in this cosmic mystery is dark energy, the mysterious force thought to be accelerating the universe's expansion. If our current models are slightly off about how dark energy behaves, that could explain why our measurements don't line up. Here's the catch. We've always assumed dark energy's influence stays constant over time, like a steady push on the cosmos. But what if it isn't so simple? Some theories suggest dark energy could be growing stronger or weaker, subtly changing how fast space stretches. Imagine blowing up a balloon. If you start blowing harder midway, its expansion rate suddenly shifts. That kind of unexpected change could throw off our calculations, making nearby galaxies seem like they're moving faster than they should compared to the ancient universe. Another possibility: dark energy might interact with matter in ways we haven't accounted for, warping spacetime differently in various cosmic eras. It's a humbling reminder that even our best theories about the universe's engine might still have blind spots, ones big enough to leave us with this baffling mismatch in Hubble's numbers. What if the Hubble tension isn't a cosmic mystery at all, but a human one? Sometimes the biggest puzzles come from the tiny, invisible mistakes we don't even realize we're making. In astronomy, these are called systematic errors, hidden biases that slip into our measurements without us noticing. Think of it like looking through a slightly warped telescope lens for years before realizing it's distorting everything you see. We've been burned before. Take the case of stellar parallax, where early attempts to measure distances to stars were thrown off by Earth's atmosphere bending light in unpredictable ways. Even today, something as subtle as dust drifting between galaxies could be scattering light, tricking our instruments into seeing distances or speeds that aren't quite real. And it's not just hardware. Data processing itself can introduce ghosts in the machine. When studying the cosmic microwave background, tiny calibration quirks or statistical assumptions might accidentally amplify or erase patterns we rely on to calculate the universe's expansion. The scary part: these errors often only reveal themselves decades later, after we've built entire theories atop shaky foundations. So while astronomers cross-check methods obsessively, the nagging question remains: could some overlooked glitch, something no one's even thought to test yet, be quietly twisting the numbers that started this whole debate? What if the Hubble tension isn't just a puzzle to solve, but a doorway to something entirely new. Cosmologists are starting to wonder if this stubborn discrepancy isn't pointing toward physics we've never seen before. Our current rulebook for the universe, the Standard Model, has been incredibly successful, but it might not tell the whole story. For decades, it's explained everything from the glue holding atoms together to the dance of galaxies, but now cracks are showing. Modified gravity is one radical idea gaining traction. Instead of dark energy, maybe gravity itself works differently on cosmic scales, weakening over vast distances in ways Einstein's equations didn't predict. Picture throwing a ball and watching it suddenly curve upward instead of falling. That's the kind of unexpected behavior some theorists are proposing. Even wilder, hidden dimensions folded into space-time could be subtly altering how the universe expands, like invisible fingers stretching reality from directions we can't perceive. Or perhaps undiscovered particles lighter than neutrinos and barely interacting with matter are zipping through the cosmos, nudging the expansion rate just enough to throw off our measurements. These aren't just sci-fi concepts, they're serious hypotheses being tested right now. If confirmed, any one of them wouldn't just fix the Hubble tension. It would rewrite physics as we know it, revealing a universe far stranger than we ever imagined. That first fraction of a second after the Big Bang might hold the key to this whole mystery. The universe didn't just expand, it exploded outward faster than light itself during a mind-bending phase called cosmic inflation. But what if inflation didn't play out exactly how we've assumed? Tiny irregularities in that hyper-speed stretch could have left fingerprints on the cosmos, subtly warping the expansion rate we measure today. Think of it like a baker kneading dough. If there were uneven patches in that early cosmic stretch, they'd leave hidden folds in space-time that still influence how galaxies move apart. We see hints of this in the cosmic microwave background. Those faint temperature fluctuations that look almost lumpy. Some regions appear hotter or colder than our models predict, as if inflation flickered in intensity like a sputtering engine. Could those ancient ripples mean the universe's initial growth spurt wasn't perfectly smooth, throwing off our modern calculations? If inflation was more chaotic than we thought, it might have seeded variations in dark energy's grip on space, creating a cosmic speedometer that ticks differently depending on where or when you look. It's a tantalizing lead. The answer to today's Hubble tension might be written in the first tremors of existence itself. Here's something startling to consider. What if we're living in a cosmic anomaly? The Hubble tension might not stem from flawed physics or measurement errors, but simply from an accident of location. Our galaxy sits in a relatively empty pocket of space called the local void, surrounded by fewer galaxies than expected. This emptiness could be tugging on our cosmic neighborhood, making nearby galaxies appear to rush away faster than they truly are, like a boat drifting faster in a quiet current while the rest of the ocean moves differently. Astronomers call this the Hubble Bubble hypothesis. If true, it means our local measurements aren't reflecting the universe's true expansion rate, just a quirky regional effect. Picture standing in a valley while trying to measure a mountain's height. Your perspective might be skewed by the dip around you. Similarly, if our corner of the cosmos isn't perfectly average, then the CMB's pristine, big-picture data and our local readings would naturally clash. Some simulations even suggest these cosmic irregularities aren't rare, meaning other observers in denser or emptier regions would get wildly different results too. It's a humbling thought. The Hubble tension might not be about the universe's rules at all, but about our limited vantage point in an enormous, uneven cosmic tapestry. Yet skepticism remains. The Milky Way's surroundings would need to be far weirder than we've observed to fully explain the tension, like a void so vast it defies typical large-scale structure. And if we are in a bubble, deeper surveys should eventually reveal its edges, where expansion rates suddenly shift. Until then, this idea lingers as a tantalizing what-if one that reminds us how much where we look shapes what we think we know. Here's a cosmic curveball. What if the universe itself is playing tricks on our measurements? Gravitational lensing, the phenomenon where massive objects warp space-time and bend light around them, might be quietly distorting our view of distant supernovae and other cosmic yardsticks. Picture a funhouse mirror stretching and twisting reflections. That's essentially what galaxy clusters or dark matter clumps could be doing to the light from these explosions as it travels billions of years to reach us. Normally, we account for some distortion, but what if it's more pervasive than we thought? A lensed supernova could appear brighter or dimmer than it truly is, throwing off our calculations of its distance. Imagine trying to gauge the height of a mountain, but the air above it is acting like a shifting magnifying glass. Suddenly, your measurements get messy. The problem gets thornier when you realize lensing isn't random. It tends to amplify light in ways that could systematically skew our data. For instance, if slightly magnified supernovae are overrepresented in our surveys because they're easier to spot, we might unintentionally bias the expansion rate toward higher values. It's like sampling only the loudest voices in a crowd and assuming everyone speaks at that volume. Some studies suggest this effect could account for a small chunk of the Hubble tension, though likely not all of it. But here's the twist. If lensing is muddying the waters, it might also hint at unseen structures, invisible dark matter halos or cosmic filaments tugging at light in ways we haven't fully mapped yet. So while lensing alone might not solve the puzzle, it forces us to ask, are we reading the cosmos clearly, or is spacetime itself smudging the numbers? Here's the problem with using stars as cosmic yardsticks. Sometimes the ruler itself might be bending. Take Cepheid variables, those pulsing stars astronomers rely on to measure distances across the universe. Their steady rhythm of brightening and dimming is supposed to be our gold standard, like a lighthouse with perfectly predictable flashes. But what if we've been misreading their signals? Recent studies suggest these stars might not be as uniform as we thought. Metallicity, the amount of heavy elements in a star's makeup, could be muddying the waters. Stars born in different cosmic eras have different metal contents, and that subtly alters how they pulse. Imagine two grandfather clocks, one built with pristine brass, the other with slightly impure alloys. They'd tick at nearly the same rate, but not quite. Now scale that up to galaxies millions of light years away, and suddenly tiny discrepancies snowball into big headaches for our cosmic calculations. Some researchers argue that failing to account for these stellar ingredients could skew distance measurements by just enough to explain part of the Hubble tension. But Cepheids aren't the only suspects. Even Type Ia supernova, those brilliant stellar explosions we use as standard candles, might not be as consistent as advertised. Their peak brightness is supposed to be predictable, tied to how swiftly they fade. Yet mounting evidence hints that their host galaxies' environments, whether rich in young stars or swirling with gas, could tweak their luminosity. It's like assuming every light bulb shines at exactly 100 watts, only to realize some are dimmer or brighter depending on the room they're in. The stakes are high. If our stellar rulers are wobbling even slightly, it throws off every measurement built atop them, like a game of cosmic telephone where each step amplifies the error. That's why teams are now racing to recalibrate these tools, peering deeper into stellar physics than ever before. Because in a universe where distances are everything, the slightest misstep in understanding the stars could mean we've been measuring the heavens with a broken tape measure all along. Here's a twist that might surprise you. Some of the universe's tiniest particles could be throwing our cosmic calculations into chaos. Neutrinos, those ghostly subatomic particles that barely interact with matter, might hold a clue to the Hubble tension. Billions of these invisible particles are streaming through you right now, unaffected by walls, planets, even entire galaxies. For decades, we assumed they were massless, zipping through space at nearly the speed of light. But now we know they have a tiny bit of heft, and that changes everything. even a slight neutrino mass alters how structures form in the cosmos. These particles were so energetic in the early universe that they smeared out matter, preventing galaxy clusters from clumping too tightly. Picture sprinkling sand on a trampoline. If tiny vibrations shake the surface, the grains won't pile up in the same way. If our models underestimate neutrino masses, we might be misjudging how fast the universe expanded during those critical early moments, throwing off the CMB's predictions compared to modern observations. But there's more. Certain theories suggest neutrinos might not act alone. They could interact with dark matter or even among themselves in ways we haven't detected yet. Imagine invisible threads connecting these particles, subtly tweaking how gravity pulls matter together over billions of years. If true, this could mean the universe's expansion history isn't as uniform as we thought, with neutrinos quietly tilting the cosmic scales. While they're unlikely to explain the entire Hubble tension alone, these elusive particles remind us that even the smallest players in physics can have universe-sized consequences. And with next-generation detectors hunting for neutrino secrets, we might soon find out just how much they've been shaping the cosmos behind the scenes. Here's something that might bend your mind literally. The shape of the universe itself could be warping our cosmic calculations. For years, we've operated under the assumption that space is perfectly flat, like an endless sheet of paper stretching in all directions. But what if it's not? Even a subtle curvature, like a gentle saddle or a barely perceptible dome, could throw off how we interpret the universe's expansion. Think of it like measuring distances on Earth. If you didn't account for the planet's curve, your maps would slowly drift into inaccuracy. The Planck satellite, our most detailed map of the cosmic microwave background, initially suggested the universe is flat to an incredible degree of precision. But dig deeper, and there are faint whispers in the data, hints that space might have a slight bend after all. If true, this could mean light from distant galaxies has been traveling along warped paths, subtly altering our perception of how fast they're moving away. The stakes are high. A curved universe would rewrite some of Einstein's foundational rules, tweaking how gravity and dark energy interact over cosmic scales. Imagine a ball rolling across a tilted table. It would accelerate differently than on a flat one, and so might the universe's expansion. Some theorists argue this could bridge the gap between the CMB's slower expansion rate and today's faster measurements. Others counter that Planck's data is too precise to ignore, leaving the flat universe camp firmly entrenched. Yet the debate isn't just academic, it's a reminder that even the geometry of reality might be up for grabs. Because if the universe isn't as flat as we thought, then our ruler for measuring everything, from galaxy clusters to the Hubble constant itself, might need a fundamental recalibration. And until we know for sure, this cosmic curveball keeps the Hubble tension alive, proving that sometimes the answers aren't just in the numbers but in the very fabric of space. What if the very laws of physics aren't as constant as we thought? This isn't just wild speculation. Some cosmologists are seriously considering whether fundamental forces might be shifting over cosmic time. Take gravity, for example. Newton's gravitational constant, big G, is treated as a fixed number in every equation, plugged in with unwavering confidence. But what if it isn't so unchanging? Imagine if the universe's glue slowly weakened or strengthened over billions of years, subtly altering how galaxies move apart. Suddenly, the Hubble tension starts to make sense because we'd be comparing expansion rates measured with a cosmic ruler that's been quietly stretching. The idea isn't entirely new. Decades ago, pioneers like Paul Dirac toyed with the notion that gravity might fade over time. Today, advanced telescopes and atomic clocks let us test these radical theories like never before. If big G was slightly stronger in the early universe, it would have compressed spacetime differently, leaving an imprint on the CMB while making modern expansion appear faster by comparison. Picture a rubber band losing tension. What starts tight eventually loosens, changing how it stretches. But here's the catch. Tweaking one constant sends shockwaves through all of physics. Alter gravity, and you risk unraveling precise predictions about everything from black holes to planetary orbits. So far, experiments like pulsar timing and lunar laser ranging show no evidence of a drifting Big G, but the margins are razor thin. A tiny, undetected change could still lurk within the noise, and gravity isn't the only suspect. Even the fine structure constant governing electromagnetism's strength has faced scrutiny. Some quasar studies hint it might vary across space and time, though results remain hotly debated. If confirmed, it'd mean the universe's rulebook isn't written in permanent ink, but in pencil, quietly edited by forces we don't yet understand. While mainstream physics clings to constants, the Hubble tension keeps this fringe idea alive. Because when two impeccable measurements clash, maybe the problem isn't the data, but the assumptions we've etched in stone. Until we rule it out definitively, the haunting possibility remains. The universe's laws might be more fluid than we ever dared imagine. Imagine the universe as a cosmic web, not a smooth, uniform expanse, but a tapestry woven with vast, empty voids and dense threads of galaxies called filaments. These structures are so enormous they could be tugging at spacetime itself, creating pockets where the universe expands slightly faster or slower than the average. Here's the catch: if we're sitting in one of these over or under dense regions, our local measurements might not reflect the true cosmic expansion rate. Picture trying to measure the ocean's tides while bobbing in a whirlpool. Your readings would be off because you're stuck in a local anomaly, the most intriguing possibility. These voids aren't just empty space, they might be actively pushing galaxies apart. Dark energy's repulsive force works more strongly where matter is scarce, meaning voids could act like cosmic accelerators, stretching space faster within them. Meanwhile, dense filaments might resist expansion, creating a patchwork of speeds across the universe. If our corner of the cosmos leans slightly emptier or fuller than average, it could explain why nearby galaxies seem to speed away faster than the CMB predicts. Yet the math isn't so simple. For voids to fully account for the Hubble tension, they'd need to be far larger or weirder than what we've observed. Some simulations suggest these structures would need to stretch hundreds of millions of light years, big enough to make our local void look like a tiny pore in comparison. And if that's true, it raises another question. Why haven't we spotted these colossal gaps yet? The answer might lie in the limits of our observations. Mapping the universe's large-scale structure is like trying to trace a continent from a single beach. We're only seeing snippets of the bigger picture. Upcoming sky surveys, like those from the Euclid telescope, could finally reveal whether these hidden cosmic landscapes are quietly warping our measurements. Until then, the voids and filaments threading the cosmos remain both a tantalizing clue and a frustrating blind spot in the Hubble tension mystery. Even the most advanced telescopes in history aren't immune to tiny, invisible flaws, and when measuring the universe's expansion, the smallest calibration hiccup can snowball into a massive headache. Take the Hubble Space Telescope. Its legendary precision relies on painstaking adjustments to ensure every light sensor, mirror alignment, and filter performs flawlessly across decades. But space is a harsh environment. Thermal shifts from orbiting in and out of sunlight can warp instruments ever so slightly, like a metal ruler expanding on a hot day. Over time, even a miscalibration of 1% could distort brightness measurements of distant supernovae, enough to skew the expansion rate we calculate. The James Webb Space Telescope faces an even trickier challenge. Its infrared eyes peer through cosmic dust, but that requires calibrating against stars whose properties aren't perfectly known. Imagine tuning a high-end microscope using a reference slide that might itself be imperfect. If Webb's stellar benchmarks are fainter or brighter than assumed, every distance measurement downstream inherits that error. These aren't hypothetical risks. Astronomers have already spotted minor discrepancies between Hubble and Webb's readings of the same stars, hinting at hidden calibration wrinkles. The real trouble starts when these tiny uncertainties compound. A slight misjudgment in a star's brightness throws off its distance estimate, which then skews the calibration of supernovae used to measure farther galaxies, creating a ripple effect. It's like building a tower where each block is just a hair off-center. By the top, the whole structure leans. Teams rigorously cross-check their tools, but some biases only surface after years, or when a new telescope reveals what the old one might have missed. That's why the Hubble tension keeps scientists up at night. If even our best instruments carry whispers of error, how much of the discrepancy is real physics, and how much is just the cosmic equivalent of a fogged-up lens? Until we can rule out every last calibration ghost, this puzzle will linger, a reminder that in astronomy, seeing clearly sometimes means questioning the very tools we trust most. There's an invisible skeleton holding our universe together, dark matter. We can't see it, but its gravitational pull shapes galaxies and guides the cosmos' largest structures. Yet for all its importance, we still don't know exactly how this mysterious substance is spread across space, and that uncertainty might be quietly warping our cosmic calculations. Here's the puzzle. When we measure the universe's expansion using galaxy surveys, we're relying on how those galaxies move. But their motion isn't just about expansion. It's also about the gravitational tug-of-war with surrounding dark matter. If dark matter clumps more tightly than we've assumed, galaxies would be pulled harder, making their motion seem slower relative to the universe's stretching. On the flip side, if dark matter is smoother, galaxies would drift more freely, appearing to speed away faster. It's like judging a swimmer's speed without realizing there are hidden currents pushing or pulling beneath the surface. The trouble is, our maps of dark matter are indirect. We infer its presence by watching how light bends around galaxy clusters or tracing the orbits of stars at the edges of galaxies. These methods paint a rough sketch, but the fine details, like whether dark matter forms dense knots or wispy halos, remain fuzzy. Some simulations suggest dark matter might be clumpier on small scales than our models predict, which could mean we're misjudging how much it's influencing galaxy motions today versus in the early universe. And here's where it ties back to the Hubble tension. The cosmic microwave background reflects a time when dark matter's distribution was simpler, like a smooth fog. But over billions of years, gravity sculpted it into complex filaments and voids. If we've underestimated how much that clustering evolved, our predictions for how fast galaxies should now be moving apart might be slightly off. Imagine trying to forecast a river's flow without fully accounting for how rocks and bends reshape its current. You'd get the broad strokes right but miss crucial ripples. While dark matter's hidden architecture probably isn't the sole culprit behind the Hubble tension, it's a reminder that even the universe's most dominant ingredient still holds secrets. Until we pin down exactly how it's woven into the cosmic fabric, this shadowy puzzle piece will keep us questioning whether we're truly measuring expansion or just seeing its echoes distorted by the dark. The universe wasn't born smooth, it crackled with quantum chaos from the very first instant. During those unfathomably brief moments of cosmic inflation, empty space itself wasn't so empty. Tiny particles flickered in and out of existence, their fleeting energy imprinting microscopic ripples on the fabric of reality. Today, those same quantum tremors might be echoing across billions of years, subtly warping how we measure the universe's expansion. Here's why it matters. Inflation stretched those quantum fluctuations into cosmic proportions, seeding the uneven distribution of matter we see in galaxy clusters today. But if those early ripples were stronger or more erratic, then our models predict they could have nudged dark energy's grip on spacetime in ways we haven't accounted for. Picture blowing up a balloon with tiny bumps already etched into its surface. As it expands, those imperfections grow, altering how it stretches overall. Similarly, if quantum jitters left the early universe slightly lumpier than we thought, it might mean dark energy's push against gravity isn't as uniform as our equations assume. Some theorists argue these quantum relics could explain why the cosmic microwave background's expansion rate seems out of sync with modern measurements. The CMB captures the universe's state before matter fully clumped together, while today's observations are shaped by billions of years of gravitational tugs from those very lumps. If quantum fluctuations were more influential than we realized, they'd create a subtle mismatch between then and now, like comparing a still pond to one disturbed by hidden currents. Not everyone's convinced, of course. The math linking quantum chaos to today's Hubble tension is still speculative, requiring refinements to inflation theory that aren't yet set in stone. But if future telescopes detect unexpected patterns in the CMB's faintest whispers, we might finally trace this cosmic discrepancy back to its quantum roots, proving that even the smallest tremors at the dawn of time can shake the universe in ways we're only beginning to measure. Here's something that might upend everything we thought we knew about cosmic expansion. The Hubble constant, that crucial number describing how fast the universe stretches, might not be so constant after all. Recent studies suggest it could fluctuate depending on where, or rather when we look. The farther back we peer into the cosmos, the more this supposed constant seems to waver, like a mirage shifting in the desert heat. Take Type Ia supernova, for instance. These stellar explosions are supposed to be our most reliable mile markers, their brightness revealing exact distances across cosmic time. But when astronomers compare supernova at different redshifts, different slices of the universe's history, the Hubble constant they calculate doesn't always match up. Some datasets hint it might be slightly higher for nearby galaxies and lower for those farther away, as if the universe's expansion rate has been subtly changing gears over billions of years. This isn't just an observational quirk. If real, it could mean our cosmic speedometer is broken, or worse, that we've fundamentally misunderstood how expansion works. One possibility is that dark energy's influence isn't uniform. Maybe it grows stronger or weaker over time, tweaking the Hubble constant like a dial we can't see. Picture driving a car where the gas pedal slowly sinks deeper on its own. You'd accelerate unevenly without realizing why. But there's another twist. What if it's not the universe changing, but our tools? Light from ancient supernova travels through eons of expanding space, passing galaxies and dark matter that could subtly alter its path. If we're not accounting for every cosmic bump in the road, our measurements might get stretched or squeezed in ways we haven't caught yet. The debate is far from settled. Some teams argue these redshift variations are just noise, while others see a pattern too compelling to ignore. Either way, the implications are staggering. If the Hubble constant isn't constant, then the very foundation of modern cosmology might need a rewrite, and the tension we're grappling with could be the first crack in a much deeper mystery. Deep in the heart of nearly every galaxy lurks an invisible monster, a supermassive black hole. These cosmic engines don't just devour matter, they blast unimaginable energy back into space, shaping their surroundings with hurricane-force winds and blistering radiation. But here's where things get interesting. That violent feedback might be doing more than just stirring up galaxies. It could actually be warping spacetime itself in ways that skew our cosmic measurements. Picture a pot of water boiling furiously. The steam billowing upward doesn't just disappear. It pushes against the lid, creating pockets of pressure that ripple through the entire system. Similarly, when supermassive black holes erupt, their energy injects turbulence into the cosmos, potentially nudging galaxies to drift apart slightly faster in regions crowded with these active giants. This isn't just theoretical. Some galaxy clusters near particularly violent black holes show signs of expanded voids around them, as if space itself has been puffed up by the relentless energy output. The catch: the cosmic microwave background can't see this local chaos. It traces the universe's smooth infancy, long before black holes grew massive enough to start rearranging things. So if these gravitational powerhouses are subtly accelerating expansion in their neighborhoods today, it could mean we're comparing two different cosmic eras, one pristine and untouched, the other reshaped by billions of years of black hole fireworks. But quantifying this effect is tricky. Black hole feedback isn't uniform. Some galaxies erupt in bursts, others simmer quietly. Worse, their influence might stretch much farther than we thought, threading through intergalactic space like invisible shockwaves. Upcoming telescope surveys aim to map these energetic fingerprints in unprecedented detail. Because if black holes are secretly tweaking the universe's expansion rate right under our noses, it would solve one piece of the Hubble tension, while revealing just how much a single supermassive beast can bend the rules of the cosmos. The universe keeps two sets of books, and they stubbornly refuse to balance. On one page, we have the early universe's ledger, etched into the cosmic microwave background with pristine precision. On the other, modern observations of galaxies and supernovae scribble a different story in ink that's still wet. This isn't just a minor accounting error. It's a fundamental mismatch between how the cosmos behaved in its infancy versus what we see today. Think of it like trying to predict an adult's height from their baby photos. The CMB is that baby picture, a flawless snapshot from when the universe was just 380,000 years old. Based on those early proportions, we'd expect today's expansion rate to unfold at a certain steady pace. Yet when we measure nearby galaxies, the numbers jump higher, as if the universe hit an unexpected growth spurt. The deeper we look, the clearer it becomes. Something shifted between these cosmic eras, rewriting the rules of expansion when we weren't looking. Part of the challenge comes from how differently we observe these epochs. Early universe data is like examining fossilized footprints perfectly preserved but frozen in time. We extrapolate forward using physics we're confident about, like gravity and dark energy's push. But late-time measurements are messier, tangled up with galactic collisions, dark matter's invisible scaffolding, and even the way light bends across billions of years. It's the difference between studying a single drop of water under a microscope versus trying to chart the currents of the entire ocean, the real puzzle. Both methods are rock solid in their own domains. The CMB's predictions match exquisite precision for the first few billion years, while supernova measurements nail the modern expansion. But somewhere in the cosmic middle, the thread connecting them snaps. Some theorists argue dark energy's strength might have shifted during this gap, like a car switching to a higher gear unnoticed. Others wonder if gravity itself plays by different rules across such vast timescales. Whatever the answer, one thing's clear: the universe isn't just expanding, it's evolving in ways we're only beginning to decode. What if dark energy isn't just pushing the universe apart, but doing it with a force that grows stronger over time? That's the spine-chilling premise behind phantom dark energy, a theory so radical it could rewrite the fate of everything. Unlike ordinary dark energy, which acts like a steady pressure stretching space at a constant rate, phantom energy would amplify its own effect, making expansion accelerate faster and faster. Imagine blowing up a balloon where each breath makes the rubber stretch easier than the last until eventually it all rips apart. This isn't just cosmic doom-mongering. If phantom energy exists even in small amounts, it would leave fingerprints on the Hubble tension. The cosmic microwave background assumes a gentle, unchanging push from dark energy, but phantom energy would have started subtle before gaining strength like a snowball rolling downhill. By now, its kick would make modern galaxies appear to flee faster than the early universe's predictions. Exactly the mismatch we're grappling with. The implications get wilder. Phantom energy wouldn't just tweak the Hubble constant, it could herald a cosmic Big Rip, where even atoms are torn apart in the far future, yet proving it's real is a nightmare. Most evidence hinges on spotting deviations in supernova brightness at extreme distances, where phantom energy's grip should be weakest. Some tantalizing anomalies in deep space surveys hint at this, but noise and cosmic dust muddy the signal. Skeptics argue phantom energy is a mathematical bandage, an exotic fix for a problem that might have simpler roots, but in a mystery where all conventional answers fall short, even the most unsettling ideas deserve a hearing. Because if the universe's expansion is truly running out of control, the Hubble tension isn't just a puzzle, it's a warning written across the sky. What if our universe isn't alone but just one page in an infinite cosmic library? The Hubble tension might be more than a measurement problem. It could be the first clue that we're living in one of countless universes, each with slightly different rules. Imagine blowing up thousands of balloons, each with a slightly different mix of air pressure and elasticity. Some would expand faster, others slower, purely by chance. Now scale that up to reality. If our universe is part of a multiverse, its expansion rate might not be a universal constant, but just a random draw from a vast array of possibilities. This isn't just wild speculation. Some versions of string theory and cosmic inflation suggest that other universes could exist with alternate physics where gravity is stronger, dark energy weaker, or even where the fundamental constants aren't so constant. If we happen to live in a universe where dark energy's push is a bit stronger than average, it could explain why nearby galaxies seem to be racing away faster than our early universe snapshot predicts. We wouldn't be seeing flawed measurements, just the natural variation of a cosmos much bigger than we ever imagined. Critics argue this idea skirts the edge of untestable science after all. How do you prove the existence of universes we can't observe? Yet the Hubble tension adds a tantalizing wrinkle. If no local explanation fully resolves the mismatch, the multiverse offers a framework where such discrepancies aren't just possible but expected. It's the ultimate cosmic shrug. Maybe our numbers don't add up because the universe wasn't designed to balance them in the first place. While we're far from definitive proof, the mere possibility reshapes how we view this puzzle. If true, the Hubble tension isn't a problem to solve, but a signature, a fingerprint left by realities beyond our own, whispering that the rules we take for granted might just be luck of the draw in an unimaginably vast cosmic lottery. Measuring distances on Earth is simple. We grab a ruler or a tape measure and get to work. But try doing that across millions of light years and suddenly the game changes completely. The sheer scale of the cosmos means we can't just stretch a cosmic yardstick between galaxies. Instead, astronomers rely on clever tricks, standard candles like Cepheid variables and Type Ia supernova objects with predictable brightness that let us estimate distances like lighthouses in a vast, dark ocean. But here's the catch. Even the tiniest miscalibration in these cosmic beacons can throw everything off. Take Cepheid stars, for instance. Their pulsations are supposed to be so regular that their brightness reveals their exact distance. But if a galaxy's dust dims the starlight ever so slightly, or if the star itself isn't quite as uniform as we thought, that introduces error into the calculation. Imagine trying to estimate how far away a streetlight is on a foggy night. If you don't account for the haze, your guess could be way off. Now multiply that uncertainty across millions of light years, and suddenly, what seemed like a reliable measurement becomes a major source of doubt. Supernovae aren't immune either. These brilliant explosions are supposed to shine with a known peak brightness, but their environments might influence their glow in subtle ways. A supernova nestled inside a dusty galaxy could appear dimmer than one in a clear region, tricking us into thinking it's farther away than it really is. Even the instruments we use to observe them, telescopes like Hubble and Webb, require painstaking calibration. A slight misalignment in the optics, a filter not quite as sensitive as expected, and suddenly, the data drifts just enough to skew the expansion rate we derive. The real headache comes when these uncertainties stack up. Each step in the cosmic distance ladder, from nearby stars to distant supernova, relies on the step below it. If there's even a small wobble at the base, that error compounds as we climb higher, like building a tower on slightly uneven ground. By the time we reach the vast reaches of intergalactic space, those tiny uncertainties have ballooned into the glaring gap we call the Hubble Tension. But here's the twist: distance measurement isn't just about tools and techniques, it's about perspective. The universe isn't static, it's expanding, warping the very space between galaxies as we measure it. That means the farther we look, the more we're peering into the past where the rules of expansion might have been different. So when we compare the ancient universe's slow, steady stretch with today's faster expansion, we're not just dealing with measurement errors, we're grappling with the possibility that our cosmic ruler itself might be changing shape. And until we can account for every variable from starlight to spacetime, the true distance between our data and the answers we seek might remain just out of reach. Here's a sobering thought: what if the universe's most familiar ingredient has been quietly throwing off our cosmic calculations? We've spent so much time chasing dark matter and dark energy that plain old baryonic matter, the stuff making up stars, planets, and us, might have been conspiring against us this whole time. It's easy to assume ordinary matter plays by simple rules, but its distribution across the cosmos is anything but tidy. Galaxies aren't smooth, evenly spaced islands. They're tangled in vast webs, clumped around invisible dark matter scaffolding. And where baryons pile up, their gravity can tug on surrounding space like invisible anchors, subtly altering how quickly galaxies drift apart in their neighborhoods. Picture a river dotted with boulders. The water doesn't flow uniformly. It speeds up in open channels and slows near obstacles. Similarly, pockets of dense baryonic matter could be creating local ripples in expansion, making some regions appear to stretch faster or slower than the cosmic average. The real headache comes when we try to compare measurements across time. The cosmic microwave background reflects a universe before baryons collapsed into galaxies, when matter was spread nearly smooth. But today's observations capture a clumpy, post-gravitational, sculpted cosmos where baryons have settled into intricate structures. If our models underestimate how much these shifts affect galaxy motions, we might be mistaking a local traffic jam for a universal speed limit. Even more intriguing, baryons don't just sit there, they interact. Gas heats up, explodes in supernova, gets ejected by black holes, then rains back down in cosmic cycles. This churn injects energy into the interstellar medium, potentially nudging galaxies apart with gentle but persistent pressure. It's like trying to measure the drift of boats while ignoring the wakes they leave behind. While baryonic matter alone can't explain the full Hubble tension, it's a reminder that even the ordinary parts of the universe hold surprises. After all, in a puzzle this complex, sometimes the most obvious pieces are the ones we've overlooked the longest. Even after all these possibilities, there's one haunting truth we can't escape sometimes. The universe surprises us with things we didn't even think to look for. Every major leap in science has come from stumbling onto the unexpected black holes, dark matter, even the accelerating expansion of the universe itself. Right now, the Hubble tension might be pointing toward another one of those blind spots, a gap in our knowledge so fundamental we don't even have a name for it yet. Think of it like this: if you asked a 19th century physicist to explain a smartphone, they wouldn't just struggle with the answer, they'd lack the very concepts needed to frame the question. Similarly, there could be forces, particles, or cosmic quirks shaping the universe's expansion in ways our current theories can't even describe. Maybe spacetime has hidden textures, or gravity operates with secret rules that only manifest across billions of light years. The fact that two of our most trusted cosmic measurements disagree so sharply suggests that something entirely outside our playbook is pulling the strings. This isn't just speculation. History shows us that when rock-solid observations clash with airtight theories, it's often the universe's way of nudging us toward a deeper truth. The discovery of quantum mechanics, for instance, came from tiny discrepancies in how atoms behaved, discrepancies that classical physics couldn't explain. Today's Hubble tension might be tomorrow's revolution, waiting for a flash of insight to reveal what we've been missing all along. Of course, unknown unknowns don't make for satisfying answers. Scientists crave precision, equations, data, not shrugs about mysteries beyond our grasp. But embracing that uncertainty is part of the journey. The universe owes us nothing after all. Every unexplained gap, every stubborn inconsistency is an invitation to look harder, think deeper, and stay humble. Because if the past is any guide, the most thrilling breakthroughs often start with two simple words, huh. That's weird. Right now, scientists are preparing to unleash the most powerful cosmic detectives ever built, telescopes so advanced they could finally crack the Hubble tension wide open. Take NASA's Nancy Grace Roman Space Telescope, launching in just a few years. With a field of view 100 times wider than Hubble's, it won't just study galaxies, it'll map millions in exquisite detail, hunting for subtle patterns in their motion that earlier telescopes might have missed. Imagine swapping out a magnifying glass for a high-resolution scanner overnight. But Roman isn't working alone. Over in Chile, the extremely large telescope, fittingly named, will peer deeper into space with a mirror nearly half the size of a football field. Its unprecedented sharpness could spot cosmic yardsticks like Cepheid variables farther than ever before, checking if they behave the same in distant galaxies as they do nearby. And here's the kicker. These instruments won't just confirm or deny existing theories, they might stumble onto entirely new phenomena we haven't even thought to look for. The stakes couldn't be higher. If both telescopes confirm today's expansion rate mismatch, it'll slam the door on measurement errors, forcing physicists to confront something truly revolutionary. But if they detect a middle ground, a slight drift in the numbers as we observe different cosmic eras, it could mean dark energy's grip on the universe is evolving, changing the game entirely. Either way, the Hubble tension isn't just a puzzle, it's a countdown. And when these giants open their eyes, the universe might finally hand us the missing piece we've been searching for. Beneath all the equations and telescope data, the Hubble tension forces us to confront something far deeper, what it truly means to know the universe. Science thrives on certainty, on laws etched so firmly they feel like cosmic commandments. But this stubborn discrepancy, it's a crack in that foundation, whispering a humbling truth. Even our most profound theories are just rough sketches of reality. Cosmology has always been a dance between precision and wonder. For centuries, we've mapped the heavens with growing confidence, trusting that each new tool would bring us closer to a final answer. Yet here we are, staring at two impeccably crafted measurements that refuse to agree, an itch we can't scratch with existing physics, that discomfort. It's not just scientific, it's philosophical, because if the universe's expansion rate isn't what we thought, what else might we have misunderstood? Think of it like a ship navigating by stars that subtly shift over time. For generations, those stars seemed fixed until someone noticed their positions didn't quite match the charts. The Hubble tension is that same unsettling moment for cosmology. It doesn't just challenge a single number, it asks whether the sky we've been reading is written in a language we've only half decoded. Perhaps that's the real gift of this mystery, not an answer but a reminder. The cosmos owes us no clarity. Every breakthrough comes wrapped in new questions, and every final theory eventually meets its limits. Right now, the Hubble tension is that limit, pressing us toward a choice. Cling stubbornly to old frameworks or embrace the thrilling uncertainty of rewriting them. Because here's the secret hidden in the data: science isn't about being right. It's about being less wrong, peeling back layers of assumption until something truer emerges. Whether the resolution comes from dark energy, gravity's secrets, or something entirely unnamed, one thing's certain: The universe, it seems, still holds cards it hasn't shown us. And that's not a crisis, it's the most exciting invitation imaginable. So where does this leave us after exploring 25 possible explanations, from shifting dark energy to hidden quantum ripples, cosmic voids to wobbly stellar rulers? The Hubble tension remains one of science's greatest puzzles. But here's the remarkable part. Every failed solution, every dead end, has peeled back another layer of how much we don't know. The universe, it seems, is still playing its cards close. Think of it like a detective story where every clue leads to a bigger mystery. Maybe the answer lies in forces we haven't discovered yet, or perhaps our tools aren't sharp enough to see the full picture. What's undeniable is that this cosmic disagreement isn't just about numbers, it's a blazing signpost pointing toward the next frontier of physics. And that's the real beauty of science. The moments that unsettle us, the data that refuses to fit, they're not failures, they're invitations. Every time we hit a wall, we're forced to think bigger, dig deeper, and question assumptions we didn't even realize we'd made. The Hubble tension isn't a roadblock, it's a launch pad. So whether you're a seasoned space enthusiast or just cosmic curious, stay tuned. The next breakthrough could be just over the horizon, maybe even in the next video. Hit subscribe and let's keep unraveling the universe's secrets together, because the greatest discoveries don't start with answers, they start with a puzzle that won't let go. And this one, it's only just begun.